Too cold. Yeah. Hey, at least you're not having to be on St. Croix and dealing with the Evans Center right now. Huh? It keeps going on and off. Yeah. And every time they think they fix it, it goes out the next couple days where it's like only working half the building. Telling you my life shifts, but it's 3 o'clock. So choose a group, H a non-empty subset of G. Property that is A times B inverse is A for any A and B, what can we say about H and G? Ooh.
That'd be a term I know. That'd be a term I know.
Well, you weren't here in class on Wednesday, so. But wrong answer is better than wrong answer.
Wait, this thing just kicked me out. Wait.
Oh, I gotta lock it right. I gotta lock it right now. What, Chris? Go, hurry!
Dude, I tried to log in, right? But it kicked me out and I like it didn't have a password or something. And then I tried to get my laptop on my laptop had a password disabled and my laptop is not connected. Give me a second. I need to restart it.
So what I'm gonna say is just so you can look, take like a corner of a piece of paper or something, just write down. The rest of you got drainage in it though?
No,
What do you want? So all I'm gonna say is just because I see just there's 2 people who submitted answers twice. You're not gonna get the choice of like, one being correct, one not. I'm just gonna choose the correct one. I'm gonna choose whatever the last answer is that you insert. So I'm gonna leave it there just for a second. I'll give everyone 30 seconds. Whatever your last answer is what I'm bringing. All right. I'll lock in 10 seconds. Chris, so you go with that answer?
yeah.
And work 5, 4, 3, 2, and 1. So what can we say about H and G?
Everything that's in H is in G.
So that is true because H is a subset of G. But we can go one step further based on what we did on Wednesday. And what can we call H? There we go, got it right. Wait, how are you muted? Sorry, Shanika, you said something. Shanika, can I get a mic check? Apparently the sound in here was muted, so if you were saying something, I didn't hear it.
Was it short?
It's this, the subsets. Okay. It is a subgroup. That was our one-step subgroup test.
That's the thing.
But we
last
said that
time.
already, it is a subset.
No, no, that's not subset.
Subset, subgroup, which so now you did, at least the last answer that I saw, you give some correct notation. I was just looking for you to say subgroup. There's a way we could note subgroup. And it's with that less than or equal to sign. You just do less than if you know you're a strict subset. So if H is not equal to G. So if there's elements that are in G, they're not in H. Let's get the broadcast going. Here. That goes away. On the lines I'm showing, yeah, so. That was that one-step subgroup test. G be a group and H be a subset of G that is not empty. It was a weird property, right? But it turns out it actually works. If I choose any two, H has this property that I choose any two elements. And A times the inverse, so the first element times the inverse of the second element is still in that set of H. Then I know H is going to be subgroup of G. Well, subgroups are still groups, right? We still have to have three important properties, which are operations associative.
Inverses and I mean identity.
Yeah, I like you to flip those, right? Because without identity element, we can't talk about inverses. So, associativity, there's an identity element, and once I've established there's an identity element, every element has an inverse. So we went through and we said, okay, well, as long as H has that particular property, then we said, okay, well, we get associativity. I get that for free, right? Because we're already working inside of a group. All associativity here is about that operation. We're still using the same operation. So we're all good there. The identity element for G also ends up being the identity element for any subgroup. Because how many identity elements can we have in any group? One. And if H is a group existing inside of G, should have the same identity element. We were able to show that. And then lastly, it was nice and easy to show that any element's inverse, any element that is in H, its inverse is also H. We already knew inverses existed, again, because we were working inside of large group G. All we needed to show is that inverse was in H. And the last thing we needed to show for the proof of the theorem was that, hey, let's just make sure we're not accidentally generating elements that are going to be outside of the set H, but still in my larger group G. We're able to show that that's never going to happen. We choose any two elements, X, Y. Its product, X times Y would be in that set H. So we could call H a group, and thus is a subgroup.
So the annotation is always gonna be the same, being less than equal to sign, however, now that we're without equal.
So it's that, and that just comes from the subset language.
Yeah.
So if H is a subset of G, there's the possibility that H and G could be the same thing. Right? But there is you deal with sets a lot. Some people give you this notation, proper subset, take kind of that line that's the equal to part, so to speak. So now this is saying H is a subset of G and H cannot be equal to G. So when it goes to subset language or subgroup language, if our subset is allowed to also be the entire set, we keep that, otherwise. H would be a strict subgroup, I guess, maybe you could say, of G. But all this is trying to do is saying that there are elements that are in G that are not. Okay. Let's get some more proofs, especially in groups. We're going to prove the following statements. If G is an abelian group, and we define the set H to be all elements in G, such that when I operate it with itself, it becomes the identity element, or you can also say it's its own inverse. Then H is a subgroup of G. So do I need to show that H is a group on its own? Yeah, I just need to employ that one-step subgroup test. So I will admit one step is kind of misleading when you look at the actual usage of it, because when I go back to it, and I know I'll bring this statement up again, there's still a condition in it. It's not in my if part, it's not in my hypothesis, but it's something I always want to confirm. So let G be a group, let H be a subset of G, and also what? H is not empty. It's got to have things in it. It can't be the empty set. Right? If I just said H is a subset of G, well, is the empty set a subset of any set? Yeah. So technically, empty set would have been a possibility. And I can make really weird set definitions that will just boil down to the empty set, even though it might not look like it would be the empty set. So the first thing I really need to do is confirm that that set H that we have has something in it. It is not empty. But then once I've confirmed that it's not empty, I can apply my one-step subgroup test.
Have you checked this into many times?
They gotta show that something's in there.
What's that method you apply to that?
There's not like a catch-all trick. It'll change from situation to situation. But I'm working inside of the group, so I know I have elements. And how is it again H defined?
All X in the group that are X for the identity.
Yeah. And what's another way we can say that? What's another way we can rephrase it? I'm just writing out our preamble. Any element that when I operate it with itself becomes the identity. Or, I will say was, if I'm operating with something becomes the identity element, it's probably inverse. So it's an element inverse. Because we also know that inverses are. So can I think of an element in a group that I can multiply it by itself, it becomes the identity element, or an element in a group that is its own inverse? Always. Not one, there's a concept of one, groups. Yeah, our identity elements. I know I have an identity element with my group G because it's group. You know, it has an identity element. We always reserve that little lowercase e for the identity element. And what happens if I take e, the identity element, and operate it with itself? So does it satisfy the definition of being an element in the set H? So my identity element is in that set H. And thus H is non-empty. Right, so I know I have a non-empty set. I know it's a subset of my group G. Always picking elements from the group G. So now I get to apply my one-step subgroup test. I need to choose any two elements. Write this as our goal again. I'll do it in green. For any A and B in this set H, we want to show that A times the inverse of B is also in the set H. So when it goes to my proof, I'm just going to let A and B be elements of H. Just choose any two elements of H. Well, if they're in the set H, what do we know about A and B?
Wait,
They're also in G. That's correct. There's something even more particular about it.
They're inverse.
They're their own inverse. We know A squared is equal to the identity element. And B squared is equal to the identity. Well, going back to the property of H, to show something is in there, I have to be able to square it, and it becomes what? Yeah, identity element. So I need to figure out what's happening to AB inverse quantity squared. Because again, for A times B inverse to be in H, A times B inverse quantity squared needs to be equal to identity element. That's how we define the set H. Ooh, this is going to be important. What I miss in my preamble of the proof that's in this statement. It's an abelian group. Sadly, what did I only give myself in my proof? It's just a group. So what do we want to go back and change? I want to change my proof. Yeah, I want to change my proof to an abelian group, right? I don't want to be restricting myself to just any group. I don't see why that's necessary here in a second. Well, now I'm in this just basic logical deduction part of my proof. A times B inverse quantity squared is just what? I don't know that yet. That's why I want to show. Because if it is equal to E, then I know it's in the set H.
and this one we could bring the two to each other, or no?
Say that one more time.
Like A squared, B inverse squared, no?
You could. I'm not sure what happened to the group if we went that way. Because this is a commutative group and you're applying the correct property of commutative groups. A squared times B inverse squared. What do you for there?
A squared is B. Here, look over B squared.
And what's the inverse of B squared? I don't really know anything about the inverse of B. I don't know if it's a group. You might be able to go back and show B inverse is also in that group. Or in that set H and getting them myself, which shows it. You can probably finagle it from. But he also eliminated a piece of bit of information. It's a good instinct. I'm not going to say it's wrong. I just don't know how to get to the end from that path. But I can keep it a little bit more simple. A times B inverse squared is AB inverse and AB inverse. Actually, did I just shortcut it and then I forgot myself? Oh, this is science tonight. One second, guess myself. We're gonna keep your work. You just see me in linear today. I was just flipping fractions randomly. Like 3/2, and I would just start writing 2/3. What was up with it today? We can definitely do something with B inverse squared.
What do you?
What are some other exponent properties that we know to be true inside of groups?
You're gonna be the negative two.
So what do we mean by B to -2 though?
But if you do B to -2, isn't that saying that the inverse is -1?
No, it's just saying I'm taking the inverse of B and multiplying it by itself twice. That's how we do it. I gotta step away from the whole negative exponents being that flip fraction. That's a whole thing that you can only do when you're doing fraction.
But interesting. She says that B inverse to the second power, she was saying that B to the -2. But wouldn't that, like, is that what we did just there? Because isn't that saying,
Yeah, those two are the same ways to write that term. B to the -2 power though is just indicating I'm just taking the inverse of B and multiplying it by itself twice.
We can multiply by the next number, right? No?
Well, it depends.
Multiply by B.
Let's see, if I multiply by B, then remember I'm doing a whole equation, right? So if I wanted to multiply on the left by B here, I'll just go back to the beginning and multiply on the left by B. Which means my initial element is not going to it's no longer going to be AB inverse 1 squared. It's that multiplied by B on the left.
B inverse is not in G.
B inverse is in G, but I'm not worrying about the G itself.
Or
I'm
H.
working with H.
B inverse not.
We don't know. I'm not sure if you can actually prove. She might be able to.
Isn't like E equals B times dash? I don't know.
I'm focusing too much on the exponents, which is what I expect to do. I want you to remember one of our important properties for groups, whether or not it's a abelian or just a standard group.
Is equal to B negative 1.
B inverse. A inverse. And when we wrote that property for inverses inside of groups, A and B's are just representing buckets of something, right? It can be elements of the group G and another element. Or they could be the same elements. I have things written on the right hand side of that equality here. I have the inverse of an element times the inverse of another element. So I can take that equality going from right to left. What is that going to give me? This is B inverse. But wait, I have B times B. And just B squared. And what do I know B squared is equal to? E. So really, this is just the inverse of E. What is the inverse of my identity? Identity element? No. So I was able to consider A times B inverse quantity squared through a string of equalities. I showed that it's just equal to what elements? Identity element. So does that satisfy the property of being in the set H? Yes, it does. Therefore, AB inverse is in the set H, and by our one-step subgroup test. Yeah, this set H, the subgroup of G. The trickiness with abstract algebra, we have to learn how to view the objects. What are the different languages that you view? This is part of the reason why, like when I teach algebra, and you get, and you're trying to say like, this right here. What would you tell me that this function is doing?
Square the number, adding in.
Square the number and adding one. Does it care what the number is? No, it's just a placeholder, and it's telling you its process of how things are going. I square a number and add one. This theorem, when we go back to the theorem when we wrote it earlier, right? A times B inverse. If I take any elements and I consider its inverse, it's the same thing as the inverse of the second element times the inverse of the first element. I don't care what those elements are. It's just telling me that if I multiply two things together, whatever their outcome's inverse is, the same thing as second thing's inverse and the first thing's inverse. So we get to start hacking away at this rigidity that we're actually stuck with when we're dealing with algebra and calculus. We have a little bit more of a free reign on our thought process and perspectives in which we can view things. You no longer have to view that table that's in front of you always from up top. You can view it from the side, you can view it from underneath, you can view it through that window while we're floating from a drone 300 feet in the air. I don't care, right? And you can learn new ways to get new perspectives on things. perspectives. And when you learn those new perspectives, it starts to unlock the different things you can do. Part of the reason why some people get obsessive with this type of math. What question do you got?
None.
Which I think means. Do one question.
Oh.
Okay.
Like, I don't understand how the inverse squared is the. Because, okay, right? I don't think of the negative one on the inverse as a negative one, it's just an inverse symbol.
Mhm.
So I don't understand how an inverse symbol could become b to the -2.
So that was a notation. That's what I was talking about with Melissa. Because when I said, what's one thing we can do with the inverse square? It's like, well, we can write it as b. What I was saying was, that's acceptable, but remember that was just a notation thing to say that we're
Okay.
taking the inverse of b. The negative there is in, and we give it inverse, and how many times it's multiplying inverse. Yeah, but I can clarify. This stuff can be confusing. Either way. I believe at least that. We're gonna do another one. Theorem. We're going to consider something called a special linear group of 2 by 2 matrices over the real numbers, which is just the set of all 2 by 2 matrices, such that the determinant of that matrix is 1. Special linear group of order 2 from 2 by 2 matrices over the reals is a subgroup. The general set is general linear matrices of 2 by 2 with real entries. Anyone remember how we define the general linear group of 2 by 2 matrices with real numbers? Give you a hint. Deals with 2 by 2 matrices.
And do you mean like when you multiply them together, you get a next 2 by 2?
No, it's the size, the number of rows and columns in the matrix. You have 2 rows and 2 columns in all of the matrices.
I was gonna say, is that a 2 or is it
Where?
inference?
Like right here? That's a 2. It doesn't have a dash through it, it's a 2. That's a dash through it. Talked about this. It was brief. There was a set of all 2 by 2 matrices with real entries. Determinant was non-zero. Or you can think of it as a group of invertible matrices. 2 by 2 matrices. All we're doing is saying, hey, look at a smaller group, because instead of just saying the determinant can be non-zero, we're specifically saying the determinant has to be what? 1. So we're going to show that this creates a subgroup. All right. You might have to flip back through your notes. Does anyone remember the identity element was for that GL group, general linear group 2 by 2 matrices of the reals? Yeah, the 2 by 2 identity matrix. And what is the determinants?
One.
Only one. Then, you know that this 2x2 identity matrix is also going to be an element in what set?
S.
Yeah, SLs. So, we know that's not it. There's at least something in it. So now that I know I'm dealing with a non-empty subset of that general linear group, I can proceed to realize this. To show that this SL is a subgroup of it, what do I need to show?
The inverse.
Inverse is involved.
What is it? The inverse in the group?
So if it is a group, it will have an inverse, right? We're trying to show that this SL set is forming a subgroup inside a bigger GL group. Well, those are one set subsets. Find two elements from the smaller set and show one.
And the inverse in the small set.
Yeah, the first element times the inverse of the second is in that set. Remember, it's always the take any two elements. Then show A times the inverse of the second is in there. That's just a general concept every single time. I take two elements. I just need to show that the first element times the inverse of the second element stays in that set. And I know it's a subgroup. Well, what are my elements here?
Nature.
Matrices. We want to keep that in mind. So let's choose two matrices from that set. And since they're coming from this SL set, what do we know about their determinants?
One is one.
They're one. So determinant of A is equal to 1 as well as the determinant of B. What can I do with that? Because really to show that I'm in SL, I don't need to show what happens to A times B inverse. I just need to guarantee what about A times B inverse.
The determinant is one.
The determinant is 1. That's how I show that it's actually in this set. So I need to show that the determinant of A times B inverse is 1. So if I consider determinant of A times the inverse of the matrix B, how can I break this up?
Would it be the determinant of A times the determinant of the inverse of A?
Yeah, we can split determinant calculations over matrix multiplication. This is the determinant of A times the determinant of B inverse. And there's one more thing that I can recall from my linear algebra courses about the determinant of an inverted matrix. How does it relate back to the initial matrix, in this case, B?
When you multiply it by the identity element.
So you can bring that in and away from. I don't want to say no at all, but I think Melissa was getting to the rule. Or maybe it was Sinaitica.
1 over determinant B.
Yeah. In general, the determinant of a matrice's inverse is 1 over the determinant of the original matrix. But what is the determinant of A?
1.
What's the determinant of B?
1.
So I just have 1 times 1 divided by 1, which gives me 1. So now what do I know about that matrix multiplication A times B inverse?
It's in.
The SL. Yeah, that's fine if we say SL. That's a mouthful to say otherwise. Therefore, B inverse. Thus, because it passes the one-step subgroup test, you know, a subgroup of a general linear group order 2. I've got my little black square. So what questions do y'all have? A lot easier than showing something this. Well, we can always find random subgroups, but there's going to be some particular subgroups that are going to be of interest to us and of interest to groups in general, especially if we can get to something called the Chinese remainder curve. You might have heard reference before. Better leave that there. We're going to find something new. Because after we deal with groups, even if we don't have commutativity, we could probably find that there is some element in a group that will still commute with any other element in the group. Not just the idea, not just certain inverses, but there could be random things that work that way. So we say, let's go ahead and make that its own collection. Let's make a collection of elements that commute with any other element in that group. So the center of a group G which is going to be denoted as a capital Z of the group G. With the set of elements of G that commute with all other elements of G. That is, if we want to look at a set definition. See if G is all elements in G such that A times X is equal to X times A. For all A in my group G. And one of the interesting things about this is that the center of any group also forms another group. Let G be a group, and the center of G forms a subset of G. Or subgroup, sorry, I said subset. And also, if you think about it this way, I'm saying within any group, there is a what group? Abelian group. An abelian group is made up of all the elements that commute with everything else, which means we'll also commute with other elements inside of the G instead of G. So within any group, I can always find an abelian. Now that abelian group might not be interesting, because it might just be a single element, but it's always there. We can start the proof. Might get it done today. Let G be a group, and I am guaranteed there's always going to be one element in that group that will commute with any other elements, even if it's not an abelian group. What is that element? Yeah, the identity element, G. My identity elements in G. And we know that X times E is equal to E times X. For all elements in that group G. Then my identity element is always going to be in the center of my group. So I know I'm always going to be non-empty. In practice, that might also be the only element that does commute with every other element. You'll know. But still technically an abelian group. But now that I've shown that this set that we have called the center of G is non-empty, shows a subgroup, what do I need to do?
A times B in group. Again.
So we're not going to be able to do it today, so let's just talk about it, right? Again, one step subgroup test says for any two elements. In that set, we achieve the center of G. We need to show that the first element times the inverse of the second element is also in the center of G. Well, if A times the inverse, the first element times the inverse of the second element is in my group G, that means it needs to what with every other element in G? It needs to commute. This means I need to show that AB inverse times some element X is the same thing as X times AB inverse for all X in the element of G. Question is, how do we show that? Well, what do I know about A?
They have inverse. And
Has an inverse in the group, if that's you're right. I know something even more about. Because where did this little a come from?
it comes from.
Yeah. It comes from the center, which means it commutes with anything. Is B inverse in the set G?
Yeah.
Yeah, so it can commute with B inverse. It can commute with X. So I could quickly move that A over to where I want it. Can I do anything with B inverse? Can I commute B inverse?
No.
No. It's weird though. I do know B inverse commutes with at least one thing, or two things technically. The identity element and what else? B. And technically also itself, B inverse. Because if I go back to my definition of an inverse, it's B times B inverse is equal to B times, or B inverse times B equal to the identity element. So you get that B inverse B, the same thing as B inverse. And flip it. So what we're gonna do on Monday. Let's see. We're gonna show that as long as A is in there or B is in there, inverse is also gonna be in. Which means its inverse also commutes, which means that I can quickly rearrange this left side of this equation to be the right side of this equation. But I have to show B inverses. All right, don't forget, homework is due tonight. Okay, I don't know, I mean, if you send me an email asking for help, I'll try to, but I don't know how late I'll be late. I'm still kind of sleep deprived from this week, so I might crash early. So, you know, if you're emailing me at like 11 o'clock, I might not be able to respond.
I would have one question.
So yeah, we'll ask after class, so just so you start recording, but if you don't have questions for me, feel free to get on out of here and I'll see you.
All right, have a good one.
You too.